In this pencast, we're going to look at section 11.5, which is really the introduction of Taylor and Maclaurin polynomials. And it starts off with what I think we already remember is the definitions of the Maclaurin and Taylor polynomials, excuse me, in the beginning of the section. If we look particularly at the Taylor polynomial, I think that's easier to recognize that this part of it right here that I'm circling is the linear approximation formula that we used in section 3.6 for the tangent line approximation for a function output. Now, if we erase that box and look at this, and I think we dealt with this as the local quadratic approximation. I think we called it a tangent parabola. So instead of having a tangent line approximation, we have a tangent polynomial, second degree polynomial approximation. And I believe I mentioned, and now is the time, to show that that does generalize to sort of an infinitieth degree or an nth degree polynomial for any point of tangency right here when you see the phrase about x equals x sub 0. X sub 0 is the point of tangency, and then the rest of it plays out. Remember, because we're generating a polynomial, this x is that x. That stays a variable because what you get at the end is a polynomial. So the polynomial has to have its function variable x. X sub 0 is, of course, our point of tangency. And then the function output would be here first, and then we have the first derivative right here, and then the higher order derivatives. And everything else is formula-based. Later on in this pencast, you'll see how to generate Taylor polynomials of any degree just based on given information about function output, point of tangency, and higher order derivatives. A nod to Maclaurin polynomials simply says that when x sub 0, let me change colors, when x sub 0 is 0, then the Taylor polynomial that we see down here simplifies out to this, because in all cases the x sub 0 is 0. So if we kind of put a 0 here and a 0 here, I know it looks like I'm circling it, you'll see that everything simplifies out from the Taylor polynomial to the Maclaurin polynomial. So to reiterate, the Maclaurin polynomial is a special case of the Taylor polynomial. Slide, I took all the markings off. If we look back at the previous slide, particularly focusing on the general term right here for the Taylor polynomial, or since I did it in blue, the Taylor polynomial for the Maclaurin, the general term for the Maclaurin polynomial, look at those, and now let's flip up. See that the red sort of nth function term for the Taylor polynomial here, now look at the blue. We could do it one more time. Blue, red. Now, although these definitions look intimidating, if we flip back to this slide, and let's look at blue is the Maclaurin, that now is on the bottom, that's confusing, and the red one, being the Taylor, is on the top. Now if we flip back and forth, then we see the red general term for the Taylor series. And same with the blue, look at the blue, I'll pause, okay, blue, red. So all the Taylor series and Maclaurin series are the series definitions of the polynomial. Because since polynomial is really the expression with all the terms added, if the terms follow a pattern, which they do, then they can be expressed using k as a series rather than n as a polynomial. No big deal. The term, the behavior, the necessary information is all the same. It's simply expressing a polynomial as a series. These now are what I like to call the College Board Big Four. E to the x, sine x, cosine x, and 1 over 1 minus x. I can say nothing except commit these to memory. Somewhere in typically the multiple choice section, somewhere they will say what is the series, what is the sixth term of the Maclaurin series for sine x, or something that relies on your simply knowing these. So to reiterate, commit them to memory. So if we have e to the x here, this is the series. Might not be a bad idea to memorize the general term so you can generate the series when necessary. So sine x, here is the series terms here, and then the general term right here. cosine x down here. Here are the series terms and the general term. And lastly, of course, we have 1 over 1 minus x. There's the series, there's the general term, and here's an interesting definition or way to remember it. When you're dealing with this function, it is, as it says, happens to be a geometric series with the initial term of 1, so a equals 1, and r equals x. Keeping that in mind and applying what you know about geometric series, it's easy enough to generate the series and the finite or infinite sums if necessary. The important part is that you need to recognize at least I would say the general term definition for each series better if you have memorized or the pattern or some way to kick out the first 4 terms of each series, like realizing that e to the x, okay, it's 1 plus x squared over 2 factorial, x squared 3 factorial, all pluses. Okay, that's easy. Sine x, what do we have? Just the odd powers of x over the corresponding factorials, starting at x to the first and then alternating. I don't know, whatever you can do to commit it to memory and be able to recognize the series would be to your benefit. And that's it. Section 11.5 in its presented materials, pretty basic, particularly with previous exposure for Taylor and Maclaurin polynomials. So now we're on to examples. Now, I know I'm starting with example 5. You can read the other examples, and I believe they're simply like generate the terms, or, you know, what's the Taylor-Maclaurin polynomial for this easy function, or they're deriving the big 4. I honestly forget. But example 5 is one that's not one of the big 4 or not painfully obvious. So we're given a function and we need the Taylor series about x equals 1. So we know that x sub 0 in this case is 1, and the function is, it's probably better to express it as x to the minus 1, so we can use the monomial rule for the higher order derivatives. Okay, to do problems like this, you just generate the, I don't know, first 3 derivatives, plug it into the formula that's given right here, and let's see what it looks like. So if f of x is x minus 1, let's do some derivative work. So f prime of x equals what? Negative x to the negative 2. F double prime of x equals 2x to the negative 3. F triple prime of x equals negative 6x to the negative 4th. And that should be more than enough, 24x to the negative 5th. And then let's start plugging these in. I cut the summation off on this graphic. This is k equals 0 to positive infinity. So we start at k equals 0, and we kind of ask ourselves, what is the 0th derivative? Well, you can reasonably conclude that the 0 derivative is simply the function output. So the Taylor series looks like first function output. So now we're going to take all of these derivatives here on the left, plug in 1, and see what happens. So here I have f of 1, and that's going to be 1. So f prime of 1 equals negative 1. F double prime of 1 equals 2. F triple prime of 1 equals negative 6. And the 4th derivative of 1 equals 24th. So now let's start assembling our Taylor polynomial. So it starts with the 0th derivative, which we're going to consider the function output. X sub 0 is 1, so 1 goes here. And then these are your corresponding factorials. Keep in mind that 0 factorial by definition is 1. So our first term is the function output 1 over 0 factorial, parentheses, x minus your point of tangency to the 0th. Now we just keep going. So the next term, we're going to add to it f prime of 1, that's in the numerator, so actually I'm going to switch that plus sign to a minus sign. So that's going to be 1 over two factorial. Oh, k equals 1, sorry, 1 factorial. 1 factorial, x minus 1 to the first. So we're done with this. We're done with this. Let's go on to k equals 2. So we're going to add to that. The derivative output is in the numerator, 2. The corresponding factorial, and corresponding meaning corresponding to the k term. K is 0, k is 1, k is 2. So I have 2 over 2 factorial, x minus 1 squared. So the exponent is also corresponding to the k value. One more, I think I have room to squeeze in one more. So the third would be negative 6. So that's going to be minus 6 over 3 factorial, x minus 1 cubed. And then I suppose you could just go plus dot dot dot, but I think it's cooler to actually simplify these and look for a general term, or at least a simplified expression. So let's see, 1 over 1 is 1, x minus 1 to the 0 is 1, minus, what's that, 1, so x minus 1 to the first, you can put the 1 there if you'd like, plus 2 over 2, that's 1, x minus 1 squared, minus 3 factorial 6, so I have x minus 1 to the third, plus onward, k equaling 0, k equaling 1, k equaling 2, k equaling 3. So our general term looks like it's x minus 1 to the k. You wish it was that easy. I'm sure you noticed by now that we have this alternating plus or minus. So that means we need what we saw in expansion by minors last year. We need an alternating factor. So we're going to put negative 1 here, and we just have to set the exponent so that it makes the operator plus and minus as appropriate. And I believe it is going to be just k. Let me double check that. Got it, got it. Yeah, life is good. This is the general term, and if you wanted the actual terms here, you could just do that with a dot, dot, dot. Depends on what the directions ask you, but I don't think it's a bad idea to get into the habit of kicking out the first 3 terms, 4 if you need it. We had the information for the 4th term, but it was pretty obvious by the 3rd term, and then maybe a general term, and you're on your way. Easy peasy. This one I thought was interesting just because it doesn't look like you have anything to sink your teeth into. So which of the functions graphed in the following figure is most likely to have that as its second order Maclaurin polynomial? The Maclaurin polynomial means the point of tangency has to be x being 0. Not a problem, as it doesn't specify what the y-coordinate is. So the Maclaurin polynomial does not have to go through the origin. We're just looking at the point of tangency being x equals 0. So here, here, and here. So the Maclaurin polynomial for its second degree has to match the behavior of the function in the neighborhood around the point of tangency. Well, this is simply 2x squared minus x plus 1. That has a y-intercept of plus 1, upward concavity. It's a parabola like that with a y-intercept of positive 1, which has a corresponding x sub 0 value of 0, and it's concave up. Clearly, it's that. Because for the second degree behavior in the immediate neighborhood, just like the tangent line approximation, it has to behave just like the function. And if you look through the textbook in the section, there are pictures of functions and then these higher and higher and higher order Taylor or Maclaurin polynomials. And the higher the order, the closer they match the function in the neighborhood. So we can assume that this polynomial matches the original function, which we're looking for in the neighborhood around x equals 0. And it is number 4. And lastly, when you have given information, can you generate the, what are we looking for in this one? The Taylor polynomial, because x sub 0 is not 0, it's 1. So with given information, can you generate the Taylor polynomial? It is, like we said, plug and play. So we're going to call this the 0th derivative. So that's going to correspond to this term right over here. So it's looking like the Taylor polynomial starts with 2, and I'm going to minus the first derivative value given to me, negative 3. Since it's the first derivative, we're over 1 factorial, and the binomial, because we're constructing a polynomial, has an exponent of 1. Then I'm going to add to that the second derivative value, which is 0. I know the term is 0, but I'm just going to go ahead and put it in. 2x minus 1. The exponent and the factorial follow the corresponding value of k. Looks like we're going to go 6 for the third derivative output over 3 factorial x minus 1 cubed. And when we simplify that, we get 2 minus, what's that? Oh, I was, sorry, it's plus. So minus 3 quantity x minus 1. And then plus, that's going to be 0. So then we're going to go plus, that's going to be 1 x minus 1 to the third. And that's it. We can't really go on further than that unless we try to find a way to generate some arbitrary constant. That would be odd. This is to the first. This is x minus 1 to the 0th. So it looks like the binomials are progressing by every other integer, right? We got 0, we got 1, we got 3. Nah, I'm going to skip the general term and just stop right here. I can't think what I would do with the arbitrary constant. And of course I had to stop and look at the answers because I was curious. And yeah, the textbook does offer this sort of continuing general term past k equals 3, and it looks like this. K equals 4 to positive infinity, c sub k, x minus 1 to the k. So if I kind of erase this, you can add a summation to an existing set of explicit terms. You just do that. And that's saying, hey, well, we just continue with x minus 1 to the k, because we have it. This is x minus 1 to the 0th, x minus 1 to the first, x minus 1 to the second, x minus 1 to the third. And if you're thinking, hey, x minus 1 to the second isn't there, so you can't go x minus 1 to the k, you can, because of this being an arbitrary constant. So in this spot in the series, 4k equals 2, c sub k equals 0. We didn't say that the arbitrary constant couldn't be 0. Don't you just love arbitrary constants? They've been fun all year. So this one has an interesting example of, okay, I have enough information for the first 3 terms, and I'm just going to add on the summation to say, if you wanted more, you could do it, but you do have to throw in a term for the arbitrary constant. The fact that the arbitrary constant can be 0 takes care of any quote-unquote missing terms if the binomial is not there. And you don't know what's going on because the function's not given to you. They just give you some function outputs. So that's a wrap on 11.5.